So here's a new word, electronegativity.
Yeah.
You like that one?
It sounds exciting.
It sounds exciting, doesn't it? Electronegativity. Yes, question.
The two ways that they bond electrons, one about sharing electrons.
Sharing or transferring? Transferring electrons would be the ionic bond. So electronegativity is the ability of an atom in a molecule to attract the shared electrons to itself. So if we go back to the little boys playing at each other's houses, it's the coolness factor of the house. Fluorine's house just had all this fun stuff. So it's more electronegative. It's more attractive to little boys, okay, more attractive to electrons. So if we talk about a molecule HX, where X is just some element and H is hydrogen, the relative electronegativities of those two atoms are measured by comparing the actual energy of that bond with the expected energy of the bond. Okay, so the actual energy, we talked about we mentioned bond energy. Bond energy is the energy required to pull those apart. Okay? The expected bond energy is what we would predict just based on sizes and other things. And so when it's stronger than we expect, then we see that there's electronegativity differences there.
Do we actually do that?
We do not in this class, but people do, yes. Scientists do. On the periodic table, there are trends in electronegativity. It generally increases as you go across a period. So reading across the periodic table from left to right, the electronegativity increases. And if you go down from top to bottom, it's going to decrease going down. The range of electronegativity values is from 4 down to 0.7. That's an arbitrary scale. They just said, well, let's make the most electronegative one 4.0, and everything is relative to that. And we're not going to get hung up on the numbers. Let's see. Hopefully there's a periodic table. Okay, so here is a periodic table that shows the electronegativity values for these different elements. And this is, really nice. But what do I want you to know about this? I want you to remember that fluorine is the most electronegative element. So here's fluorine. So they're giving us the numbers here, but it's also kind of a topographical map. As we go this way, we're getting higher. The elevation is higher. The electronegativity is higher. And so fluorine over here up in the upper right corner is the highest. The noble gases aren't on this periodic table, are they? The noble gases pretty much don't form compounds, and so for electronegativity, we just ignore them. It's like you bunch of loners, just stay over there. Yes?
The scope of height, what is hydrogen?
Um,
Is it like the same as carbon?
well, they stuck hydrogen over here, and hydrogen has the same, it's a 2.1, it has the same electronegativity as phosphorus. And, like we've mentioned before, hydrogen just has to be an exception to everything. Did you have a question?
Is that what inert means because they don't have this?
No, inert means they don't react. They don't react. And electronegativity is not what drives reaction, but in order to figure out electronegativity, you have to look at the expected bond energy and the actual bond energy. And for a compound like helium that doesn't form any bonds with anybody, there's nothing to compare. And it's irrelevant anyway. So that's why those guys are missing. So if you remember that fluorine is the most electronegative, then all you have to do is say, well, if you're comparing two elements and saying which is more electronegative, which one's closer to fluorine? So say you were comparing iodine and chlorine. Which is more electronegative? Well, chlorine is because it's closer to fluorine. Or if you're comparing selenium and zinc, selenium's closer to fluorine, and so we expect it to be more electronegative. Those trends are not absolute. There's some exceptions in there, like from palladium to silver, from gold to mercury. there's a decrease that we don't expect, we're not going to worry about that. We're just going to say fluorine's the most electronegative. If it's closer to fluorine, it's more electronegative than the one that's further away. So if lithium and fluorine react, which has more attraction for an electron? So we look at the periodic table. We got lithium way over on the left side, and fluorine, which we were just talking about, fluorine's the most electronegative.
Fluorine.
Fluorine is going to have more attraction. Why?
Closer to fluorine.
Because it's closer to fluorine. Because it's more electronegative, right? So if the fluorine, let's see if there's an answer here. No, there isn't an answer. So then I'll write the answer. You know, they're just surprising slides to me. Fluorine. And this is an example of a two-part question. Students like to ignore the why or explain, and teachers really get bent out of shape when you do that. So, you know, even if you just write some nonsense, that's better than leaving it blank. Fluorine, because it's more electronegative. Electronegative. So in a bond between fluorine and iodine, not lithium, iodine now, which one has more attraction for an electron? So again, we look at the periodic table. We look at the periodic table all the time. You have a question?
Morning. What I was going to ask you, out of your two-part questions, like
Mhm.
how many students would you say skip the second part?
How many students skip the second part on two-part questions? I'd say probably about 25%. Yeah.
So good chunk.
Good chunk, yeah. And see, the thing is, a question like this, the answer to the first question is a 50-50, right? Lithium or fluorine. You could guess that, right? Well, I'm not going to give points to people for just guessing junk, right? I want to know, do you have a clue about what this is? And this situation doesn't show up on an exam because they give multiple choice exams, but on a lab, perhaps, or in the homework. And just in general, in life, you know, if you're filling out a form and there's one box there, but they ask you to put two things in there, if you want whatever you're applying for, you better put both things in there, right? I mean, this is one of these little character things. You go apply to transfer to different colleges and stuff, or you apply for a job, and if you blow off details like that, it says something about you. Okay, and it's not something good. It doesn't say anything good. So if we are looking at fluorine and iodine in a bond, which has more attraction for an electron?
I know.
Yeah, devil's advocate over there. It's going to be the fluorine. Why? Because it's more electronegative. See above. Ditto. It's the same answer. Because it's more electronegative. Okay? Oh, there's the answer. Fluorine and fluorine.
They didn't answer well.
No, they didn't. And I do have an issue with that. So what's the general trend for electronegativity across rows and down columns? Okay, so I don't think it's helpful to remember across was up and down was down or something like that. You look at the periodic table, fluorine. Okay, as I go across, am I getting closer to fluorine or further away? I'm getting closer, so electronegativity increases. So across rows, I'll figure this program out eventually. Across increases, and down, if I go down, it decreases because I'm going away from fluorine. So if I go down a column, electronegativity decreases. Explain the trend. Okay, we're not going to do that.
I hate questions like that.
Well, yeah.
I would say it goes.
Because I just told you.
Because
See,
at the level of understanding that I'm requiring for you, if I did, if we were going to do that, explain the trend. Well, we learned that fluorine is the most electronegative, and going across, you're getting closer to fluorine, and going down, you're getting farther away. That's a very simplistic explanation, which is not worth me asking you to spit out. Electronegativity becomes important when we're talking about bonding. And so here in these funky illustrations, on the left, figure A shows an illustration of a covalent bond between identical atoms. These have the same electronegativity. Which is more electronegative, carbon or carbon? They're the same, right? Because it's the same element. So if you have two atoms of the same element in a bond, they have the same attraction, and so they're going to share equally. Those two little boys are going to go back and forth, and they're going to split their time pretty evenly. And so that bond, in terms of where the electrons are, is going to be pretty symmetrical. Here's an example where we have one that's more electronegative and one that's less electronegative. And so it becomes lopsided. And the electrons are lopsided towards the more electronegative one. And so this end is a little bit negative, a little negative, that's a negative sign. And this one's a little bit positive. We call that a polar covalent bond. This we call a covalent bond, or sometimes, just to be clear, we call it a non-polar. Just to be clear that we're not being just general, we mean non-polar covalent bond as opposed to the polar covalent bond. And then we have an ionic bond, where here the attraction of this one for the electron, the difference in attraction here is so great that this actually keeps the electron. So this is where the one kid's house is just so unsatisfactory that he actually leaves that family and becomes adopted by the other family. And if they move to Texas, he goes to Texas with them. Okay? He becomes part of that family. This is just ridiculous, isn't it? I'm making this all up as I go along. And sometimes it just turns out kind of bad, but
Could you have a positive side being more, bigger? I know you're showing that side.
we're showing that this negative side is bigger because we're illustrating the electrons, and that there's more electron density over here than there is over there. Now, are all negative ions larger than positive ions? No. But we're not looking at the size of the atom, we're looking at where the electrons are. So that's a good question.
The polar is, it's more draw to one side.
Yeah, so really there's not a hard line between here. We don't say, well, you're covalent, nonpolar covalent, you're exactly sharing equally, and then bang, this one is sharing it unequally, but they're all the same, and then way over here is ionic. It's a continuum. And so you have some that are in the middle where they're a little bit lopsided, and here where they're getting more and more lopsided, and then where do you decide, well, now it's ionic and now it's not. So there's no hard and fast line, and so we just kind of arbitrarily put some lines in there. So the relationship between electronegativity and bond type, which we kind of already talked about. So here's the same illustration again. Here you've got the hydrogen atom and the hydrogen atom, and they're going to get together and form a molecule. And they're sharing their electrons, and this is all nice and symmetrical because the two hydrogen atoms are the same. They're going to have equal attraction, and so this is going to be a nonpolar bond, and things are going to be sharing equally.
When would that
Mm-hmm.
happen?
So you need to ask sooner because now I can't go back.
Sorry.
That's okay.
So, you have one hydrogen atom?
Mm-hmm.
In what situation would you have one hydrogen atom separated from one hydrogen atom?
Well, hydrogen does not like to be separated because, I mean, it's like a very small child and it should not be left alone, right? It's going to get picked up by somebody else. And because of the energy thing, it's not favorable energy-wise for a hydrogen atom to be alone. And so when it comes in contact with another hydrogen atom that's alone, they say, hey, let's get together and share and we'll be better. We'll be lower energy. Can you have hydrogen atoms by themselves? Yeah, but they're going to react quickly, so you can't just, have a bottle of hydrogen atoms in the stockroom and expect it to stay that way. Does that answer your question? Kind of. You want to ask a different question?
No.
No? Okay. So we're supposed to arrange the bonds from most to least polar. How do we do this? Well, what we're going to do is we're going to look at the periodic table and just kind of guesstimate the difference between the electronegativity of these different atoms. So in this series here, everything's bonded to fluorine. And so we know that fluorine's the most electronegative. And so then we're going to look at where is carbon, where is oxygen, where is nitrogen relative to fluorine on that periodic table. So we see that carbon is the farthest away, nitrogen's in the middle, and oxygen is the closest to fluorine. So oxygen and fluorine are going to be more similar in their attractiveness to electrons. So their bond is going to be less polar than the others, right? Because here we've got, fluorine with this crazy cool house, and over here, this guy's got a pretty cool house too, but he doesn't have the soda fountain. They've got 2-liter bottles, and mom will cook you a, take and bake pizza from Costco or something, won't call in. But is that a real big deal? You'll spend a little more time at fluorine. You see there's a little bit of a difference in attraction, but not a lot. And so oxygen and fluorine is going to be the least polar because their difference in electronegativity is the smallest. So oxygen, fluorine is going to be over here. We're going from most to least. Which one of those remaining, the carbon and the nitrogen, which one has the lowest electronegativity? Carbon. Carbon's farther away. So you can't see the periodic table from where you're sitting. That's why you got it wrong. Carbon is farther from fluorine. And so the carbon-fluorine bond is going to have the biggest difference in attraction. That's going to be the most polar. And then that leaves the nitrogen-fluorine to be in the middle. And this is the sort of question that could show up on an exam. And it would give you, different choices, and you pick out the correct ordering. And that's how you do it. Any questions?
So it's looking for the greatest polar opposites.
Yeah. Which two are the most different? Which two are the most similar? So the ones that are most similar will be the least polar, because if they were identical, they'd be nonpolar. So I don't like the animations. Okay, so here's another one. Carbon, fluorine, nitrogen, oxygen, and silicon, fluorine. This one's a little harder. So we look at carbon and fluorine on the periodic table, and we're like, okay, well, carbon is 3 squares to the left of fluorine. And we look at nitrogen and oxygen. They're right next to each other. And they're between carbon and fluorine.
But you know that one's last, right?
So that one has to be less polar than the carbon-fluorine. Do you see that?
Well, then either two, right?
Well, we haven't looked at the silicon-fluorine yet. It's easiest if you compare two things first.
Oh, so you can't just say they both have fluorine? So it's...
Well, you could start with those two and see which one's greater. I just happen to start with the first two. So I look at carbon and fluorine, I find them on the periodic table. They're in the same period, in the same row, and they're apart from each other. And I look at the next one is nitrogen and oxygen, and those two elements are between carbon and fluorine. So the difference in electronegativity between nitrogen and oxygen must be less than the difference between carbon and fluorine. Does that make sense? So I know that carbon fluorine is greater in polarity than nitrogen oxygen. Now I'm going to look at the silicon fluorine one and see, well, how can I relate that to these other ones? Well, there I've got fluorine. Let's look at the carbon fluorine versus the silicon fluorine, because that's easier to compare. The silicon is also to the left, which is less electronegative than fluorine, but it's below carbon, so it's even less electronegative than the carbon is. So this one must be the greatest. So it's going to go the silicon fluorine, and then the carbon fluorine. That's supposed to be a greater than sign. And then the nitrogen oxygen. Any questions? And then there's another one. Chlorine, chlorine, boron, chlorine, or sulfur, chlorine. Well, one of these is completely nonpolar. Which one is that? The first one. So the chlorine, chlorine must be the least polar. So I'm going to just write that over here. Chlorine, chlorine. Those are identical. So the other two, sulfur chlorine and boron chlorine. Well, boron is way to the left of chlorine, and it's up one, so that kind of offsets that a little bit. But sulfur and chlorine are right next to each other. So what's a reasonable guess as to which has the larger difference? The boron chlorine, because they're farther apart from each other in the periodic table. So then we would say it must be the boron chlorine with the greatest and the sulfur chlorine with the intermediate and the chlorine chlorine with the lowest. Okay, any questions? Basically, you're looking for how far away are they on the periodic table?
Who's the furthest?
Who's the farthest away? If they're farther away, there's greater difference in electronegativity. I guess you could think of it like a town, and fluorine has like the best house in the best position in the best neighborhood. And things just kind of go downhill from there, maybe literally downhill. And, and if you're way far on the other side of the tracks from where fluorine lives, that's, very, very little attraction for the little boys. I don't know. So there are the answers. And no good, we got them right. So which of the following bonds would be the least polar and yet still be considered polar covalent? Are there any of those bonds that are not polar at all? The oxygen-oxygen. So it wants a polar bond, and yet it has the least polar, and yet still has to be polar covalent. So this one's out because it's not polar covalent. Are there any others we could eliminate because they are not polar covalent? Magnesium and oxygen. What kind of a bond is that? It's ionic. So that one's got to be out too. So then we're comparing carbon oxygen, silicon oxygen, nitrogen oxygen. We look at the periodic table and see which one is closest to oxygen. It's the nitrogen. So this is the one with the least electronegativity difference. So it's the least polar, and yet it is still polar. Any questions? There's the answer. Oh, there's another one. Which one would be the most polar without being considered ionic? Well, these are the same bonds that we looked at in the previous one. Magnesium oxygen, they're just asking a different question. Magnesium oxygen is ionic, right? And oxygen, we're looking for most polar, so that one's definitely not the most polar. That's the least polar. It's not polar at all. So we've got nitrogen oxygen, which we determined earlier was the least, and carbon oxygen or silicon oxygen. Which is farther away from oxygen, carbon or silicon? Silicon. So that's going to be the most polar, but still be covalent. Okay, we'll save 10.3 for Friday.
We're finishing last week.
Sorry, 12.3.